Sean, how you doing?
Hi Chris, yeah, not bad.
Good. I can
A
see.
bit warm here.
Yeah, tell me about. Oh my gosh. As I was just mentioning to you, I've got a fan just out of shot here, and I'm clinging to it. I don't think I could do this without this fan. It is very hot. Although, of course, the Vancouver team had it even hotter until, what was it, 3 weeks ago. So I don't think we can complain too much. So yeah, here we are. So this is the second Calico Live session. I suppose we should do our introductions again. My name's Chris Tompkins. I'm a developer advocate at Tigera, and I champion our users' needs and our contributor community's needs, and try to make those voices heard in the organisation. And I've worked in networking since around 2000. I used to do kind of per device CLI traditional network configuration, and lost interest in that because it's so painful, and got interested in automation in all its forms, and that's where we are here, and that's how what led me to Tigera. I'll let you introduce yourself, Sean.
Sure. So I'm Sean Crampton, distinguished engineer at Tigera, responsible for looking after the data plane, eBPF data plane, the IP tables data plane, and various other components in our stack.
Awesome. So we should say what Calico Live is. It's an occasional informal video stream series. On that subject, we will actually have one next week is the current plan, which is a faster cadence than usual, but that's because I've got a bit of annual leave in August, so we're trying to get one extra one in. So we'll have that. And it's an opportunity to kind of relax and talk about our open source tools in a kind of more relaxed and informal setting. I've got one eye on the YouTube chat, and we're happy to be derailed. So anything, we do have a plan, of course, but if we get derailed by questions of any level, that's absolutely fine. And I've kind of got that over here, so I'll try and keep one eye on it. And there's no kind of threshold for questions. We're happy to take anything at all, and we can always redirect it. This set of sessions, we're going to be talking a lot about the eBPF data plane and digging into it. So those of you who were with us last week, last session, you'll have seen that we did an introduction to the kind of net filter flow on a node, and talked about what eBPF is and where it hooks in. We'll resist the temptation to do that again, because otherwise we'll just duplicate ground. So what I will do though is I'll just try to pull up a browser window to see if I can do this. So if I flick that over, yeah. So this is a diagram you created, Sean. So I'm sure you're very familiar with it, which kind of shows before. When a packet arrives in a node, any Linux node, including a Kubernetes node, before it gets to netfilter pre-routing, it goes through XDP and gets to a TC ingress node, and that is where our BPF programs attach on an ingress hook called the class act hook, and then there's a pre-routing, netfilter pre-routing after that. So that this is a good opportunity to kind of say, if you're unsure about any of this stuff, I published a blog post on the Project Calico blog just a few days ago, which dives into this in great detail, so you might find that interesting. Yeah, so Sean, one thing I thought was of interest here is that where that BPF program attaches, I know that there's the class act hook, which is the one that does nothing. You called it a no-op hook, which I liked, which does nothing unless we attach to it, right? What other hooks would you expect to see there?
Yeah, so probably worth saying what the TC subsystem is for. So that's the TC stands for traffic control, and it's used for things like traffic shaping. Generally, that was its original purpose. So you have packets coming in. It has ways to classify packets, and those are sort of built into TC. I mean, it has a kind of tree structure, and the packet comes into the tree and consults various rules, and then the rules can, like the nodes in the tree can have children, and the nodes are of sort of various types. And it's in charge of things like bandwidth shaping and kind of like grouping traffic into priority levels, that kind of thing. So it's where you would define your queues if you wanted to have 3 priority levels and have different queues for each one. So you could say this is high priority traffic and it should go into the high priority queue, and that queue should be processed. If the that queue you should always take packets from that queue, even at the expense of dropping packets from the other queues, that kind of thing.
Yeah, I'm looking forward to getting. Oh, sorry, you go ahead.
That's its original kind of area, and the way the mechanism works. So I'm not super duper familiar with TC in general and all those little nuances, but the class act, the name of the class act QDISC comes from classifier and action or actor, something like that.
Action, I believe, from when I wrote the blog.
Yeah. So one of the things that you want to do in TC is classify the traffic. Is it the high priority traffic or is it the low priority traffic? And the BPF hook was originally added to TC to enable you to do like interesting classification. So the BPF program gets a look at the packet, and it's a program, so you can do arbitrary calculations on there and say, if the IP address is odd, make it high priority, or if I've seen 17 packets this second from that location, mark it as low priority, or whatever. You can do whatever you wanted to do there. And then the BPF hook grew in capabilities. Has more BPF helpers added to it, and it's become more and more interesting what you can do in that hook. So you can do things like directly act on the packet, modify the packet, redirect the packet to another interface, those kinds of things that start to make it really useful for building a data plane.
And this is what you were teaching me when I first learned about this. Those are all implemented as helpers in the kernel, aren't they? Helper functions.
Yeah, exactly. So yeah, just to recap, each BPF hook is like a little sandbox, and the way it can sort of have effects on the outside world or affect the packet that's flowing through that's triggered the hook is by calling helper functions, which the kernel exports to the BPF program, and so it's by default its sandbox can't do anything. So if you want to be able to kind of manipulate the packet or act on the packet in some way, then you need a helper function that lets you do what you need to do.
Yeah, makes sense. One thing I'm really looking forward to when I dig into this a little bit more myself, because I want to dig into actually writing some code myself at some point when I get a moment. And the tree aspect of this is something that's interesting to me because I haven't dug into the code myself. I get the concept of the tree, but I want to see how that's implemented and understand it better. If I flick to the egress, is there any difference in... So the egress queue does it have exactly the same set of... Sorry, the egress QDISC, does it have exactly the same set of helpers as the ingress, or are they subtly different?
Yeah, I think at the BPF level they're extremely similar. I think all the helpers are the same. Yeah, can't think of any differences off the top of my head.
Cool.
The other behaviors of TC, the queuing and prioritization and so on, I'm not really sure if there's a big difference between ingress queues and egress queues and that sort of stuff.
Yeah.
But for the most part, Calico's just throwing in the class act QDISC queuing discipline. That's what the tree is made of. Is the nodes in the tree are queuing disciplines, and basically we don't want to influence the kind of native queuing discipline. We don't want to replace it with something different, but you can add this class act QDISC into the tree that is just there to let you attach a BPF program onto it, basically.
Yeah.
So it doesn't kind of influence the other kind of queuing and classifying, unless that's what you're unless your BPF program is classifying the packet, which is not something that our BPF programs do. They're more on the action side, manipulating the packet or sending it somewhere else, that kind of thing.
Yeah, it seems quite elegant actually. I was reading TCP dump uses BPF now, I believe, and Wireshark, I think. I'm not 100% sure about that, but I believe they do, which makes sense.
I think that's the history of BPF. It came from that type of packet filtering, where you want to be able to tell the kernel, send these packets to me up in user space. So classic BPF, the thing that came before eBPF, that was a big use case for it, if not like the driving use case, I think might have been that.
One thing I really like about these sessions is that we can go off-piste a little bit. One thing I remember bothering me when I was kind of doing a traditional network engineering job myself was the fact that the more you accelerate a packet, the less you can get visibility of it. Single root I/O virtualization and all these kind of advanced NIC features, it becomes increasingly hard to see the frame as it really appears on the wire. I remember I may have told you before about a case where I had a NIC that was intercepting LLDP frames and not delivering them to the operating system because the vendors of the NIC had decided that was a good idea. So yeah, it can be a bit tricky. Obviously, the more performance you add. So what I've actually got for us today as well. Let's see if is that readable. Yeah, it doesn't look too bad. Let me zoom in a bit. I've got a little proof of concept cluster that we'll jump on to look at in a minute. I used this in my blog post a few days ago as well. So the IPs have subtly changed, but the concept is that we've got my laptop at the top and the internet, a GCP Google Cloud load balancer, and a cluster running eBPF, a cluster with 5 nodes running eBPF. The 5 nodes have a VXLAN encapsulation, and they've got direct server return turned on, which is why if you look at this return path, it goes straight out from the pod, from the node hosting the service pod. And then there's just a simple deployment of a single node, single Echo server pod, and the reason for that was just to kind of force the traffic to move in a predictable way for my blog post, so it's not such an issue for us today. But I thought we'd take some time to do two things: to look over the settings that we need to make sure are in place on the cluster to make it perform well with BPF, and also I thought then we could dig into some kind of visualization and troubleshooting tools, and these are things I spoke about in my blog post, but I thought that you are closer to them arguably, so you're quite likely to have some observations that I don't around that, so I thought we'd dig into that if that's alright.
Yeah, fine by me.
Before I do, let's have a look at these other slides and just see if there's anything we should dig into here. So this is interesting. This is just the flow through BPF, and the thing that it draws attention to here, which I think we haven't spoken a great deal about before in these sessions, is what the maps are. So when the BPF programs want to, well, let me tell you how I think it is, and you can tell me how it actually is. When the BPF programs need to store state, essentially, a BPF map is just a data store that they can store state in and look up later. But that's not where the policy is stored, is it? The policy isn't actually implemented in maps, is it? It's implemented in policy programs that have been pre-generated, is that right?
Yeah, that's right. So BPF maps, the word map, at least to kind of programmers, conjures up a key value store where you have some kind of key and you're looking up some kind of value, and that's a good impression for BPF maps. That's what most types of BPF map are. So the simplest form is a hash table, and the BPF maps can be accessed from the BPF programs. They can also be accessed from user space. So that's one way that you can get data to and from your BPF program dynamically, while the program itself stays the same. There's also some I would say, because the kernel helpers for working with maps are already predefined, there's been a little bit of shoehorning where some new features have been added to BPF, and they've made them look like maps even though they're not really maps.
Nice.
Like they don't have that key value aspect. So they've used the API for some other things. So if you do get into BPF coding, just be aware that the kind of core maps are maps, and then there's a handful of types of map that, in air quotes, that are more specialist, and the underlying data structure is something quite different to a map.
With my very limited amount of programming, that immediately makes me nervous about them performing differently or something like that. Are they quite reliably? Do you find some lookups take longer than other lookups and that kind of thing, or is it reliable?
So I think within a particular type of map, you have a specific lookup behavior that you can expect. Most of the maps that we use are just the simple hash table map, and they perform pretty consistently, irrespective of size and so on. I think they perform fairly consistently when I've had a look at it. There's a specialist type of map that does a longest prefix match, which is the function that you need to do like routing, essentially. So we do use that for we use it for routing. We also use it for implementing what we call IP sets, which can contain more than IPs. So we've kind of done the same thing as the kernel here. We have a concept called IP sets inside Calico, which was originally based on the concept of an IP set in the Linux IP tables data plane, and then over time we've grown that further so it can contain subnets as well as IPs and various other things. So we use that to represent represent IP sets, and there are some special case types. Like there's a type that, while it uses the maps API, is actually like a ring buffer that sends data up to user space, for example. It's totally different. It's really hard to call that a map, just kind of the API has been reused for other things because it's quite convenient, and from an API point of view, it's fine. You just have to know that it's a special case. And it's not like computer science history is not littered with APIs being used for slightly different purposes than they were originally intended. It's even at my depth of knowledge, I can probably name a few of those. You just said something though that I'm glad you repeated, because I was meaning to come back to it. So what's the use case for wanting to be able to see what's in the IP sets from user space? From not the IP sets, excuse me. For seeing what's in the BPF maps from user space, apart from the obvious debugging or something like that? So we use it a lot for debugging. Also, one of the big uses that we have for BPF maps in our data plane is to store connection tracking information. So when a connection comes in, the first packet of a connection arrives, we allocate a connection tracking entry in the BPF map based on the 5 tuple of the packet, so the IP addresses, the ports, the protocol, and we use that to track the progress of the connection, and to spot when it moves into bidirectional established mode. At that point we accelerate the connection and sort of bypass further policy checks and that kind of thing. So that's a big use, but that connection tracking map needs to be garbage collected. So Felix, our agent, scans that periodically to clean up the the aged out entries and that kind of thing. There's also a type of BPF map that is called an LRU map, so least recently used, and that kind of ages out entries itself. So if it gets full, then the oldest entries get discarded.
Ah, interesting.
But I think when we first started the BPF data plane, the LRU map logic was bugged, and it wasn't suitable to use to age out our entries. So we went for like manually aging out.
Right.
I can't remember exactly what the issue was, but it was something to do with like if you ever looked at the entries from user space, all their timestamps got reset or something like that. So you couldn't rely on the timestamp. Like as soon as anyone looks at it, then the timestamp gets reset, and you might age out the wrong thing if your map gets full. That's something on those lines.
Yeah, nice. Yeah. That I was going to ask you. Actually, I'll tell you what. Let's move on, because I have a question that's related to that, but I think it'll make more sense when we're actually looking at the real cluster. So sorry. Go ahead, Sean.
I don't think I answered your question about the policy programs. Happy to.
Yeah. Go for it. Yeah, definitely.
Put that through. So the BPF data plane has sort of a few jobs to do. Like one job it needs to do is to parse the packet, so get the 5 tuple out of the packet, and then it needs to do its connection tracking lookup. Then it needs to, like, if there's a miss in the connection tracking lookup, it needs to consider whether it needs to NAT the packet. So maybe it's a service IP in Kubernetes, and we need to redirect it to the backing pod. That's one of the things that we take ownership of in our data plane. And then it needs to apply policy to the packet. And then finally it needs to kind of wrap everything up. If the policy passes, store off the contract entry, all that kind of stuff. Now most of those things can be handled with static BPF code that is just looking in a map, doing a lookup, and then you have, like, if you get a hit in the contract map, we jump over to this bit of code, and then that bit of code tries to redirect the packet along the fast path, or whatever it has to do. But policy in Calico, we already had a policy model before we implemented the BPF data plane. So Calico has Calico policy. And when we looked at
Sean, I'm going to cut in on that just for a really quick, because I think it's a really important point. I think that goes back to what we've talked about data planes before, and how the fact that you already had that model meant that you didn't have to reinvent any of that. You had the policy model. All you had to do was re-implement it in a new data plane, which is kind of a point that we've made in several talks. So I think it's worth pointing out. Sorry, go ahead.
Yeah. So when we came to implement the policy model and we analyzed it, Calico's policy model is quite rich, and we have a number of features in there that are quite tricky to implement just by reading from maps and having static code that reads from maps. So one of the limitations of BPF is that, well, at least when we started, couldn't have a loop in your BPF program, and even if you can have a loop, like whether or not you can, there's a limited number of instructions that you're allowed to have in your BPF program before the kernel says no, this is too big. So
that's interesting. So you can have a loop. It's just that if your loop overshoots the number of iterations, then you're in trouble. Is that it?
Yeah, that was a feature that they had to add. So initially loops were just forbidden. The current state of play is that loops are allowed, but the kernel's verifier, the static analysis verifier, has to be able to prove that the loop terminates. So if it's a simple loop, like a for loop that says, for I equals 0 to 100, then it will be able to analyze that loop and spot that it will definitely terminate. Yeah, certainly when we started, loops weren't even allowed. And so if you think of the Calico policy model, it's defined as an ordered policy model. So we have ordered rules, and you can have an allow rule that says allow this, and then a deny rule that says deny that, and then another allow rule that says okay, but allow these things, and they're processed in order. So the first one to match wins. And if you try to turn that into a set of maps, you either end up needing a loop that can be arbitrarily long because there could be arbitrary amounts of policy, or you need to do a very, very heavy transformation of our policy model into like something that you can do a lookup on in a BPF map. And I prototyped that sort of approach, and like I wasn't really happy with the sort of algorithmic complexity and stuff. Like it was quite a heavyweight algorithm, and it's sort of just at the limit of possible. Probably you can do it in most cases, but we're quite hampered with what features you can add to the data plane later. And it's quite possible for Calico policy to blow up from, you have 20 rules in your policy, but then once you mangle it to make it into an efficient lookup from a map, you end up with 10,000 rules in your 10,000 entries in your map or whatever.
So that's if you that's if you had implemented it through maps, but instead
exactly. So we took a different approach, and instead we write most of the BPF programs in C, like all the kind of complicated bits, parsing the packet, doing like NAT, key proxy function, contracting, responding with ICMP messages when that's required, that kind of thing. But for the policy, we use a feature of BPF called a tail call, where one BPF program can invoke another BPF program, sort of stop its own execution completely and jump to another BPF program.
Is that related to the tree structure aspect that we were discussing, or is that different? That's conceptually different.
Yeah, so the TC would have one node, and it would call one BPF program, and that BPF program can then call off to other BPF programs, and TC is none the wiser here.
Right. Okay.
And that's a general feature of BPF that you can use in several of the hooks. So what we do is we process the packet, parse the packet, we do the contract. If the contract gets a hit, then we handle that all in this C program that runs initially. So the fast path is all kind of statically compiled and done ahead of time. But then if we get to the point where we need to do a policy decision, we don't do it like that. We jump off to another program, and that policy program is generated at runtime. So Felix, our per host agent, has a BPF assembler inside it, and we just have some code that just directly generates BPF assembly code, or directly assembles BPF bytecode, and that's very efficient. So it can just directly generate the bytecode in a millisecond or something, and then we load that into the kernel and we put it where the first program can jump to it. So one of the special types of BPF maps is a map that can hold BPF programs for the purpose of jumping to them like this. So we drop the policy program into that map, and then the main program can jump to it.
Okay, that's really interesting. I wish I'd had that conversation with you when I was writing the blog, which luckily is correct, but there's a lot of detail there that I could have captured. But that's why we're having this session, I suppose. That's really interesting. Thanks, Sean. Was there anything else you wanted to say on that before we jumped onto a real cluster?
I'd say one thing we've really tried to do there is to keep the policy program sort of as simple as possible. So the main program, as it's described on your slide there, sets up a BPF map that has the 5 tuple in it of the packet and some other like flags and that kind of stuff. So the policy program can be super simple. All it needs to do is look up that entry in the BPF map, which is a per CPU BPF array, which is like a super fast type of map that can be used for sharing data between tail call programs. That's basically what it's really good for. So we look that up, and then we just have the 5 tuple accessible to our assembly program at 5 memory locations, and that's very easy to deal with. It wasn't too hard to make the policy programs with BPF assembly, and to make quite efficient. It does mean that there's still a limit to how much policy we can cram into the BPF data plane into one program. But it's a lot bigger than what we could do if we were compiling the programs down from C, or if we compiled the whole thing down at runtime from C with the policy kind of added to it somehow, and it was more efficient than what we could do with BPF maps.
I was going to ask you later, but it just seems so well attached to this part of the conversation, really, that is there a way that we're able to get visibility of the utilization of the available BPF map resources, kind of as some kind of by catting something in the proc file system or through SNMP or goodness knows how, but is there a way that we can get visibility of how much is used, or is there no real case for us needing to do that? When I say us, I mean someone running a cluster.
Yeah, so for the connection tracking map, which is like the most interesting one, I think Felix exports a Prometheus metric that it collects each time it does its scan. For the other ones, you can absolutely have a look at what's in the maps. There is a tool called BPF tool that you can get from the like some distributions package it and some don't, but BPF tool can be used to dump the BPF maps, and it will tell you how many entries are in the map at the end. From looking at the kernel APIs, I don't think there's a kernel API to ask the kernel how many entries are in the map without actually like listing the whole map. So that's what BPF tool does. So I think I'm not aware of a kernel API to do that.
Well, that could be one of those interesting aspects of how it's implemented, couldn't it? Yeah, sometimes some data structures you can't, depending on languages, some data structures you can't get them to count. I remember that being a thing in Python under certain circumstances. I'm just realizing that one thing I promised myself I would do after our last session, which I haven't done yet, is remind people that we're very open to questions. We haven't had any questions through YouTube yet, and I'm aware we're talking in quite a lot of depth about some really interesting topics, but just to take a sec to remind people that we're very, very happy to take questions, either deeper than what we're talking about already, or or not so deep, and not anything's fine. So anyone who's watching, because I can see we've got a few viewers, several actually, viewers. So if you've got anything, that'd be great. If not, I think we should jump on to this cluster, and we might be able to see some of these things. I can show you the things I know how to do, and you may be able to tell me some commands that I don't. So let's see if I can do this in a seamless way. Probably not. If I jump over to sharing my whole screen over here. Okay, yeah, I think that wasn't too bad actually. You should be able to see my shell. I'll just zoom it in a bit. I'm conscious through the Zoom compression that we're using, it's probably less readable for you than it is for people watching on YouTube. How readable is that for you, Sean?
Yeah, I'm going to struggle with that.
Are you? Okay, let's go a little bit bigger then. How's that? One more?
Yeah, maybe one more.
One more.
I can read it if I sort of lean right forward. But
Yeah, it's frustrating when we've been testing this that it's the YouTube compression works better than the Zoom compression. I shouldn't criticize Zoom, so I won't. I brought this up.
Bigger issue for me is because I'm also sharing a screen. I see the little tiny.
I'm glad you said that when you did then, actually, Sean. In which case, I think, yeah, because of the way we're doing this, I think if the trouble is if you stop sharing, I think your video will go out of whack. What I can do though.
Don't worry, I can see it now.
Yeah. Okay. Great. So yeah, the first thing I wanted to drill into is when I was writing this blog, I was really struck by this thing that you and I have briefly discussed, and we've taken it as a maybe action point. My doorbell's just gone. Hopefully, one of my kids can grab it. People do choose their moments. Yeah, so I was struck by the fact that there are a few configuration points that don't stop the cluster from running. Altogether, but they stop BPF from running in an optimal kind of scenario, and that struck me as something we should probably drill into, because what we don't want is almost if a cluster's failing, that then obviously people will remediate that. They'll figure out why it's failing and remediate it. But I was struck by the possibility that if a cluster's running in a degraded state, that wouldn't be a good thing. So I wanted to show a couple of those first of all. So if I jump to any of the nodes in my cluster, I just wanted to highlight those three aspects. The first one, which is the kernel version, and this is a supported kernel for eBPF, but basically the kernel has to have eBPF functionality. I won't say what the correct versions are, because it depends on your OS, I believe, doesn't it? And also I think it was backported for some distributions,
yeah,
right?
So the mainline kernel, I believe we support kernels 5.4 and above, but the Red Hat kernel team have backported all of the features that we need, so very kind of them, to one of their kernels that's based on sort of 4.18 or 4.19. Can't remember the number off the top of my head, but the Red Hat version numbers are kind of 4.18 point something -193 or something like that.
Yeah.
And you need the 193 or above version to get the extra features.
So this is why I wanted to call out this specific point, that it surprised me when I was digging into this that if you don't have an appropriate kernel, it will still run, but it'll fail back to IB tables, right?
Yeah, I think that's one of those decisions where you're kind of damned if you do and damned if you don't.
I was going to ask you about that, because there's an interest. Yeah, exactly. I can see the rationale for either scenario there. Really, at the end of the day, you want a functional cluster. Yeah, that's a tricky one, isn't it?
Yeah, I mean, just thinking about it now as you highlight it. I mean, I wonder if we should make Calico Node report not ready in that case.
Yeah, I like the sound of that.
So that at least it surfaces that something's quite wrong in your cluster.
Yeah, I think I'm behind that idea, because I just really don't like the idea of someone running the cluster and thinking they've got a feature turned on when they haven't. But I'm certainly not criticizing, because I can see how it's a tricky one to decide. But I think that sounds like a great idea to me.
Yeah, I think we followed suit from a previous feature that we'd added. So in IP tables mode, we have this XDP acceleration feature that sort of accelerates certain kinds of policy rules by putting them into the XDP hook, and that feature it uses BPF, so we use it as a little bit of a template in some ways when we're starting to build out the BPF data plane. And one of the decisions there was, if XDP doesn't work, we just fall back on IP tables, because it's kind of an optimization feature.
Mm-hmm.
So maybe that was in my mind when coding that up. I think it was probably me that made that decision.
Well, I think what you said before is, as well as, you're right though, that you're damned if you do and if damned if you don't. You can see you can easily make a case for either configuration. There's not a right answer, but I like the idea of it saying not ready, or even I don't know. Is there a way to put some interesting label on it? I suppose a label would just be overlooked, wouldn't it?
Yeah, I think so. I think Kubernetes might have richer ways of exposing, why you're not ready.
Mm-hmm.
But if we do report not ready for a specific reason, it does pop up in the kubelets, like reports for Calico Node. So in the status of the Calico Node Pod.
Hmm. I wonder if anyone watching has ever had that happen in production or ever been running, because I imagine the majority of the people watching this probably are running BPF clusters, or have at least built one. Be interesting if we get a comment about that. The other one, similar really, is the BPF file system, which we can check just by looking at them. So for anyone who doesn't know, in Linux you can type mount and you can see all your mounted file systems. And just as an aside, it seems like when you're in the cloud, you have a monumental number of interesting file systems. Goodness knows what most of those are, frankly. I see a lot of Docker stuff.
Those will be all the Docker containers.
Yeah, I see them now. Yeah, that's right. Yeah,
the containerizer you're running with.
Yeah, it's Docker, I believe. So if we just grab that, so it's more readable, you need to have this file system mounted, a type BPF and mounted here, so that. But again, this is interesting because again the cluster will appear to run healthily without that until I think you told me it's when Calico Node restarts. That's when it becomes a really big problem, right?
Yeah, that one's an unfortunate one. So the BPF file system is a place where, so when you create a BPF map, the BPF map is kind of owned by the process that creates it. So if Felix creates a BPF map, like the contract map or something, then if Felix dies before it does anything with that map, then the BPF map will be thrown away, like normal garbage collection done by the kernel. So in order to make the maps kind of persist, we pin them into the BPF file system, which just makes what looks like a file on the disk, except it's not a file, it's a special type of thing, which is a pinned BPF map. And that keeps the BPF map alive inside the BPF file system. Now it has to be created inside the BPF file system, which means the BPF file system has to be mounted. If we don't pin the maps, then if Felix restarts or if Calico Node restarts, then the maps all go away. And so we really want to pin them into the file system. But the really annoying thing is, if like a lot of the tools that we use to do the map, to deal with the maps, they will automatically pin the maps for us, and they will automatically mount the BPF file system for us. But if that BPF file system gets mounted inside the Calico Node container, rather than being mounted on your host, then when the Calico Node container restarts, the file systems inside the container get torn down, and the BPF file system gets thrown away, and then the pins inside it get thrown away, and then the BPF maps disappear. So we initially had a kind of what was supposed to be a clever solution for that, which was BPF maps only get thrown away if they're not in use by a BPF program. So we thought, what if we leave the BPF map, we don't pin the BPF maps, but we just connect them to the BPF programs, and then we attach the BPF programs, then they won't get thrown away.
Right.
And that works perfectly for like hash table maps and those kinds of things. But when it comes to the BPF jump table map, the map that we use to do tail calls, the kernel requires those to be pinned. If you don't pin them and you restart your process, it's not sufficient for a BPF program to have a handle, to have a reference to that BPF map. It cleans them up. So some of the maps kind of hang around when Calico Node restarts, but some of them don't.
Mm-hmm.
And the clever kind of just letting them live as references from the BPF programs, and then sort of repinning them after we restart didn't work, which meant we ended up with this requirement to have the BPF file system mounted.
Yeah. Do you think this should be something that also makes Node appear to not be ready, or something like that, or do you think this is a slightly different case?
Yeah, I'm kind of wondering that too. So we do try to mount it. So if you have if you install Calico with the Tigera operator, which is like the sort of new way to install Calico, where everything's kind of done for you by the operator. You don't need to edit YAMLs and that kind of thing. Then we add an init container to Calico Node, and the init container will try to mount the BPF file system if it's not already mounted. But the init container then needs the extra privileges to be able to mount something on the host, which is quite a high level of privilege.
Mm-hmm.
So the ideal thing is to have the BPF file system pre-mounted, so that we don't need to do that sort of escalation of privileges to make that happen.
Mm-hmm.
And if your Kubernetes cluster is very locked down, then you might have to do extra work to allow Calico to do that mounting if it's not already there.
Yeah.
The good news is that recent distributions tend to mount the BPF file system by default. So
even on just a vanilla Linux install, or when you oh, that's interesting. I didn't know that.
Yeah, exactly.
Is that just
that's kind of a? It's not the case for like Ubuntu 20.04 doesn't, but I think Ubuntu 2010 does. So it's
so that's quite an interesting question.
Do you think been updated yet?
And do you think that's because BPF is just getting adoption in lots of different scenarios now, other than what we do, other than what we use it for, and therefore it's becoming a smarter thing to have it mounted the whole time, or is there just no disadvantage to doing so? I suppose that's the other reason, presumably.
Yeah, I think so. I think they're starting to use BPF for the things, and yeah.
Cool, interesting. All right, great. So if we drop off the node now and back to my workstation, the final thing on the list for those points that we were discussing, the kind of the features that need to be set right in order to get optimal performance. The other thing that jumped out at me was making sure that kube proxy isn't running, which is what I've just done here, in the sense that because I've got a healthy eBPF cluster, obviously I'm looking in kube system to see if I have anything with the word proxy in it, and I'm counting the lines, and just the same remains true even if I do it in all namespaces. But really all I'm doing here is proving that kube proxy isn't running. But the reason for that is, let's see if I can say this well enough, and if not, you can dive in. But essentially, kube proxy's functionality gets replaced by the eBPF data plane, and that happens because if we remember right back to that diagram of net filter and the hooks before and after, since we, unlike the IP tables data plane where we have a series of points within the flow to intercept and work on the packet, since we can only act at the start and the end, it means that we have to replace that functionality, and obviously we not only replaced it but improved it with direct server return and source IP preservation and all that. But as a result, we need to make sure kube proxy is turned off. Without going into the scenario of what if it can't be turned off, that's on the money, isn't it?
Yeah, exactly. Yeah, so I think the key feature of Calico that sort of necessitated re-implementing kube proxy rather than having a kind of compatibility mode where we can work with it, is the Calico's host protection policy.
Right.
So like apart from protecting, workloads, pods, VMs, that kind of stuff, we can also protect the host itself. And I seem to remember, like when we kind of traced out the flows and worked out, okay, where's kubeproxy going to come in the different flows? There were flows that go through host endpoints that we couldn't handle if kubeproxy was running.
Interesting. Okay, I hadn't fully picked up on that nuance. That's cool. So then the other thing is, well, someone smart might say, well, what about in a scenario like K3s where you can't turn off kubeproxy? And I believe the reason in the case of K3s you can't turn it off is because it's implemented as part of the single binary implementation that K3s has to make it so light and lean. So in that scenario, if you can't turn it off, then in your Felix configuration you have a setting that you can apply here. I don't actually have that on my screen right now. Can you remember what that setting's actually called?
It's
hold on, I think I can get
one.
It is called
eBPF kubeproxy cleanup enabled.
Thank you, well done. Good save. I should have had that on my screen there, but I didn't. So what that essentially does is it tells Felix not to battle with kubeproxy in terms of cleaning up, right? It's basically saying, well, kubeproxy can't be turned off, and therefore we have to leave it to its own devices. Is that fair?
Yeah, exactly. So if kubeproxy is running, then kubeproxy will be writing IP tables rules. Assuming it's in IP tables mode, be writing IP tables rules to implement NAT and things like that. But Calico will also be running, and it will be implementing NAT. And Calico tends to get the first look at the packet. So Calico will see the packet as it enters through your interface, because TC fires before IP tables. So we'll NAT the packet before it gets kubeproxy's IP tables rules, and then kubeproxy's IP tables rules will never fire. And that means that if both things are running, then kubeproxy is just wasting a bit of resource, but Calico should always be kind of catching the packets before they hit kubeproxy, and it will all, like, functionally it will work. But the problem is if you stop kubeproxy, then kubeproxy will leave its IP tables rules in the data plane. So you've got a chunk of IP tables rules that do all kinds of NAT, and they get stale over time. So as you churn services on your cluster, those rules will get further and further out of date. And then you could get a situation where Calico's NAT doesn't match what kubeproxy is NATing, and then traffic comes through, it misses Calico's NAT, and then the old kubeproxy rules kind of do something with the packet that they're not supposed to do, because that service is long dead and the IPs have been reused for new pods, and it's all a big mess. So you could get in a situation like that. So to prevent that, by default, when BPF mode's enabled, Calico will clean up kubeproxy's rules. So we just look in IP tables and we spot any rule that is, prefixed with kube, apart from a few rules that don't belong to kubeproxy, and then we just wipe them all out to make sure you don't get into a bad situation. So setting that flag to disable you can set that flag to disable that function, and then we'll kind of coexist with kubeproxy. It's far from ideal, because you'll put extra load onto your API server by running both, and kubeproxy will be updating its IP tables rules, which is kind of a lot of CPU to burn. So you don't really want to be doing that in production if you're using the BPF data plane, because you just be wasting a lot of resource on your cluster. And there's a chance that kubeproxy and Calico will fight over things like health ports and things like that, where they're both trying to provide health information for load balancers.
So because we're low on time, I'm happy to come back to this next week if it's a question for next week. But we might want to talk about what is the right scenario then in the scenario where you can't turn it off. But I'm happy to take that next week if you think that's better.
So I think the recommendation is, try to turn it off if you at all can.
Yeah.
And I think even with setups like K3S, it might be all in one binary, but I think they have options for turning it off. There are a couple of platforms where you can't turn it off because it is baked into the cloud provider.
Right.
And in those scenarios, you just have to live with that. That sort of dual.
I might see if I can take that to try to answer that at the start of next week's session. It's specifically in the K3S case, because if what you're talking about is burning some extra CPU, then in a large cloud environment, that may not be the end of the world, as long as it's a fairly small percentage. Whereas K3S, the nature of the beast is that you're trying to make the best of a small bit of tin, and therefore that you really don't want to be doing that. I'll see if I can answer that. So given that we've only got a few minutes, I was just looking at the rest of what we had to cover off today, and I thought the most bite-sized piece that we should probably use now, because it's something we can fit into a few minutes, is the IP sets thing. So I have this command here. Actually, I'm going to clear my screen. No offense, but I'm going to put your and my video back behind the my share so that people can actually read what we're putting here. So this is just a glorified for loop that what this does is it gets it looks in the Calico system namespace, gets all the pods listed there, greps out the Calico nodes, because Calico is running a node on every Kubernetes node. Then it grabs the names of those, and then it iterates in a for loop on those. And what it does is it then uses Calico BPF, which is the tool. How would you characterize Calico BPF? What's the right way to say what it is?
So that's a tool that we built initially for internal debugging, to allow us to dump the all of Calico's BPF maps in a friendly format, so
Gotcha.
we can look at them. But we now ship it as part of Calico Node. So the tool's a little bit rough around the edges, but it's useful for diagnosing issues and checking that the data plane is programmed correctly.
Yeah, and if you want to see more about this, again, if people have a look at the blog that I posted a few days ago, I go into detail about this. So what we're doing is we're running it inside the Calico Node Pod, which means we don't need to install it or anything like that because it's already in there.
I'd say one thing that's a little bit weird when you run things inside the Calico Node Pod is we sort of do the K3S thing. We ship all of our tools like Felix and the other things that run inside there, like this tool. We ship it all embedded in one binary for minimized space. So that's why you've got to invoke it in this weird way where you do Calico Node -BPF.
Yes.
Rather than just running the tool. It's because it's all been shipped inside a little mono binary.
And I believe it's still possible to build and make it yourself, isn't it? You can still run it the other way if you choose to, right?
Yeah.
Okay.
You can build it if you check out the Felix repo and run a make command in there. You can get a copy of it, which you can then run on the relevant host.
Due to time constraints, I'll just quickly dig into this. So all that does is redirect std to std out so that we can grep it properly, and then we get rid of some debugging lines to make it more readable. So what we can see here, the reason we do this is because at the moment we can see that we're looking for IP sets, and we can see that none of the nodes have any IP sets, which makes sense. But what's cool is if I cat this policy, this is a bit of Calico network policy. And I apply that policy. If I have a look at it in Vim, you can see that this policy actually refers to a couple of IPs, which are ones that I was testing from. And if we run that same command again now, you can see that only one of the nodes has that IP set, and the reason's because the only node that has anything in the default namespace is that one. So if we look at that node 8N9KN, and we have a look for the pods again, but this time we don't rush, we can see that sure enough there's only one pod running in the default namespace, and we can see that it is running on node 2, and then if we look for the Calico node, node 2 is sure enough is the one with that same pod. So that's the reason why you might have caught me deleting something while you were talking a minute ago. But if we also reapply this Google Microservices demo, we're actually only doing this to get some extra things running in our default namespace. You'll see that now, because we have lots more things running in the default namespace, if we look at our IP sets again, we can see now that all of the nodes, actually not all, but the majority of the nodes need to know about that IP set. And I thought that was really nice, the implementation. Maybe we're out of time, but maybe in the start of next week's session we can talk a little bit about where that logic is being carried out. I think it looks quite elegant, and it's obviously, as we saw there, it's lightning quick as well. So we're over time already, Sean, and I'm very, very conscious of your time, so I think we have to call it there. As usual, we've just had a question when we're 1 minute over time. So
I don't have anything I need to go to. So
okay, neither do I. So let's just take this one question then, and then if there's any follow-on from this question, we can take it to the Calico user Slack. So the question is slightly off topic, but is there any reason someone might want to use the IP tables data plane on a Calico-enabled node? Any trade-off? Okay. So the main, and Sean, you might have other things to add to this. So someone's basically saying, is there a reason why we might not want to run eBPF? Yes, the obvious one is how battle tested it is, and the other one is the kernel version dependency. So first of all, our IP table data plane, has a lot of history, and it's been in production in a lot of environments for a long time. So I think although the eBPF data plane is running in production too, the IP tables data plane is arguably more battle tested. And then the other obvious reason is because of the kernel requirement. You might not always find yourself in a position where you can build a cluster with an up-to-date enough kernel to turn on BPF. Have I missed anything there, Sean? Those are really the main two, aren't they?
Yeah, I guess the things that you sort of went through today as well. Like if you're in an environment where you can't disable kube proxy, you might not want to take that trade-off. And we're still maintaining both data planes and have no plan to stop maintaining the IP tables data plane. So it's still, like you say, it's battle tested and used in, I think, millions of nodes at this point. So it's very solid, and the BPF data plane, we're improving it over time, and it's getting more and more battle tested over time. So.
Yeah, and on that point as well, I've done a couple of pieces about this already, but yeah, we kind of view data planes as offering a particular feature set, and there's not really any one right solution for all environments. So yeah. All right, well, I think we should wrap it there. We're a little bit over time. Thank you for coming in with a question. I appreciate that, especially being the first person to put your head above the parapet. Takes some bravery, so I appreciate that. I really enjoyed that, Sean, as usual, and we'll pick up where we left off. There's a couple of things on the agenda that I put out that we just didn't get to, but that's because I like to think that's because we were digging into other interesting details. So with that, I guess we'll pick up where we left off next time.
Cool.
Great. Speak to you later on.